Good afternoon, everyone, and welcome to today's Battery Excellence Seminar. We are happy to welcome our today's speaker. This is Dr. Sandrine Lyonnard from CEA Institute in Grenoble in France. And before Sandrine shares her knowledge with us, I would like to give you a short overview on the importance of the high throughput experimentation techniques in battery research, especially in identifying the new novel battery materials and the concomitant interfaces in the battery systems. So the title of my talk actually is the high throughput experimentation in design and development of battery materials and interfaces. And as you all know, the majority of challenges that arise within the battery research and development have to do with identification of active and inactive materials that are vital for the operation of each battery cell, as well as different cell design and then cell assembly and different protocols and conditions under which the procedures and the cycling has been conducted. And actually it all boils down to the optimization issues, which means it's like a proverbial search for the needle in a haystack, having in mind that batteries are rather quite complex systems and that we have a lot of interconnected variables that in the end dictate and govern the main processes and the main operation of each battery cell, together with the safety, sustainability, and last but not least, the costs. And in the end, it all comes down to the optimization of so-called, let's say, the observable set, and find the optimal value of an observable set in a function of variables x, y, a, b, or c. So the question is how we do this. There are several approaches to address this issue, and the first one is the so-called classical or iterative process, in which we take a so-called quasi-random walk in order to find the optimum of the observable set in the variable space defined by variables x and y. So how do we do this? Actually, we start from an educated guess, let's say like a randomized position here. Then we perform an experiment, then we analyze the results, and then based on the data we have gained, we try to understand which direction we should follow next. And this task is actually repeated multiple times until we find a so-called maximum. The good thing with this approach is that the number of experiments is limited in nature. However, we might get trapped in finding only the local maximum, as you can see here that we don't get the whole variable space covered. And having them in mind that we have sequential nature of the experiments which follow each other, this means that actually some of the experiments might take longer than the other ones. For example, if we take in consideration the galvanostatic cycling experiments that they can even take for weeks or months, then this means it's quite time intensive. And as we only cover the small part of the variable space, we get a limited knowledge gain on the system as a whole. The second process is so-called brute force approach. And as you can see here, actually, we have the complete variable space covered in a grid and characterized in order to find the optimum value of the observable set. This approach is very easy to plan, as we don't need any preliminary knowledge on the system, and we get the full picture on the variable space that we are taking in consideration. However, although this approach contains some parallelization in experimentation, it is rather quite intensive. And the most challenging part actually has to deal with the dimensionality, as we are considering the multi-dimensional space, so to say, in which we very easily end up in a so-called combinatorial explosion, when the number of the experiments exceeds the realistic proportion and the realistic expectations that we can achieve with our experiments. This means that number of required experiments goes to the power of dimension. And if we consider this the specific case here, we have two dimensions, actually two variables, and we can see that actually we already need 100 measurements. And if we consider the third dimension, then we end up with 1000 measurements. So to ease and let's say to try to accelerate the identification and search for promising battery materials and also concomitant materials, and with this to achieve a good performing battery cell and good cell chemistry, actually the question arises, why not letting the machine do all the work? And this is where high throughput experimentation comes into play. However, it is not as easy as depicted here in the picture, as in the nutshell, the goal of the high throughput experimentation actually is to parallelize automated repetitive tasks as much as possible, so that the time of researchers can be used and spent more effectively. And high throughput experimentation is a process of scientific exploration, which involves lab automation, effective experimental design, and rapid parallel or serial experiments. Often it requires robotics, rigs, semi-automated kits, multi-channel pipetters, and some other tools. In the effective high throughput experimentation work actually requires an appropriate IT and informatics infrastructure in order to fully capture the data in a so-called fair compliant fashion, which means findable, accessible, interoperable, and reusable data. And there are, of course, multiple advantages for implementing high throughput experimentation, which of course includes the greater reproducibility, innovation, and efficiency. And in order to put it in a short words, this means high throughput experimentation is ideal for accomplishing more with less and doing this in a much faster way. And as you know, by doing the high throughput experimentation, we generate an enormous amount of data from those experiments. And now the question arises how to deal with those data, and those data can actually be used for the machine learning and artificial intelligence orchestrated analysis. And of course, the high throughput experimentation is being conducted in a standardized and automated way. So the data are getting acquired, processed, evaluated, and analyzed. There are several approaches in respect to high throughput experimentation in respect to the synthetic aspects and characterization aspects on different levels, comprising battery component level and battery cell level. And here I would just like to briefly mention the high throughput experimentation workflow for battery electrolyte discovery, because each high throughput experimentation facility is unique in its design and nature. And still in literature, most of the information on the design is actually scarce. So in this workflow, actually, we start from electrolyte components. We do the full automated electrolyte formulation, cell assembly, and then following a certain number of different electrochemical techniques as a first filtration effect, actually, we create a so-called filter in order to try to identify the lead or hit candidates for a given cell chemistry and given cell application. And actually starting from strategy, doing then the high throughput experimentation and doing analysis and narrowing the forward and backward loops, actually we can ideally follow the lead candidate for a given cell chemistry. The facility at Münster, just in short, comprises several units. So the first one is the one related to the formulation of electrolyte. This one is fully automated in nature, and this is the end product. The vials, which are labeled with a two-dimensional data matrix code, where all relevant metadata are being stored. And this system is also used for the conductivity cell measurement, which I will address a little bit later. There is a storage and preparation part of this system, which actually correlates and combines the two systems. And the second one is related to the fully automated cell assembly. So we have 2 electrode and 3 electrode design, and all data are being managed. This means all input-output data are being managed, processed, and evaluated by so-called, let's say, custom designed software, which is called Laboratory Information Management System, or in short, LIMS. One of the modules is actually the conductivity module, and here you can see the reactivity vessel. It's like an Eppendorf reaction vessel, and the amount of electrolyte is rather small. This one is resealable, and of course, this is an in-house developed impedance electrode, or better say measuring probe, which provides reproducible results independent of the immersion depth in the electrolyte, which means that the volume of the electrolyte can be varied. And of course, this one is independent on the geometry of the sample container. So 8 of those cells are being actually placed on the measurement block, and then 3 of those blocks are being placed on one rack. 4 of the racks are being then introduced in the climate chamber, which allows us to run 96 different measurements at the same time due to the 8x12 channel multiplexer. And the temperature range is from -30 to 60, having in mind the nature of the electrolytes. And to the best of our knowledge, this module is unique in battery community. And what we are doing now, we are extending the module towards viscosity measurements and then the electric constant measurements, as well as density measurements, and finally the measurements of the transference numbers. So what kind of data we can get out of it? So far within the Big Map project, we were able to provide many different data sets, considering many different electrolyte formulations containing only one conducting salt or two conducting salts, and playing them with wide variety of solvents, co-solvents, and additives. And here I would just like to mention one brief example in respect to the variation of the concentration of the salt, the solvents, and vinylene carbonate used as a film-forming additive in electrolyte formulation, which actually resulted in 56 different electrolyte formulations, which were then measured in 7 temperatures. And for each measurement, due to reproducibility issues, at least 3 repetitions were done. For some of the formulations, even 7 or 8. And this one actually resulted in more than 1,200 individual data points. These data points were then actually used for machine learning analysis using so-called generalized Arrhenius fit, and thereafter linear regression and Gaussian progress regression, in order to identify, or better say, to find individual terms that can correlate electrolyte conductivity with the composition of the electrolyte. So just seeing the data here at the 2 representative temperatures of 20 and 60 degrees, you can see that we have domains with low conductivity values and high conductivity values. We also have domains in which we don't form stable solutions, and where we also get some anomalous behavior of the conductivity, of course, depending on the electrolyte composition. And the fact that we get different maxima for different temperature actually points out that the correlation between the conductivity and electrolyte composition is not as trivial as one would see or think, and that using the right tools for the data analysis, one can actually get a lot of knowledge on this one. So actually what the model here shows is actually that the predicted logarithmic values of the conductivities versus the experimental logarithmic conductivities, actually that the fit is quite good, and that the model predicts quite well the conductivity values for the considered electrolyte formulations and considered electrolyte composition. And now taking a closer look on the impact on the content of the individual components of the electrolyte, we might see that this model actually very well predicts the dependence of the conductivity and, let's say, the maxima and the shift of the maxima of the conductivity with the temperature. And we see here that the higher temperature, for example, 60 degrees, we need more content of the salt than compared to the low temperature. If we take a look to the ethylene carbonate, which is used as a standard cyclic carbonate for the electrolyte formulations, the state-of-the-art ones, we see that there is a dependence still, but not as strong as for the conducting salt. But what was quite surprising is that model actually predicted that vinylene carbonate that was used as an additive up to co-solvent percentage, that actually there was no effect of vinylene carbonate, which was quite surprising, having in mind that the structure of ethylene carbonate and vinylene carbonate are quite similar, having in mind the geometry. What the model could also predict in addition is also so-called outliers, or identification of unforeseen and non-trivial effects. And here you can see that for one given data set, actually the model predicted the negative value, but the experimental value actually was a positive one. So this data set was again set to the experimental evaluation, and the outlier you can see here with red or with the black line. And there you can see the rewind data, which means that actually in this time the measurement was started not from -20 Celsius degrees, but from 0, and then starting from 0 to 60 and going from 60 again to -20, we get a very good correlation. And then we see that the refined value actually gives a very good prediction. But now coming back to batteries and all the phenomena and all the processes that are taking place within each battery cell chemistry, one can conclude from this picture that it is rather batteries are rather quite complex systems. And in order to identify, let's say, and also accelerate the identification of the most promising battery component candidates, on one side, active materials as electrodes, and on the other side, inactive component as an electrolyte, one has to have in consideration all the processes and phenomena that are taking place within the cell during the operation. And actually, the victory in this mechanistic game actually goes to the scientists who are best able to piece together many bits of evidence from the synthetic, electrochemical, thermal, structural, and also analytical and spectroscopic evidences, and construct a mechanism that is actually able to provide good explanations, especially when we are talking about bulk characteristics of the active and inactive materials, and especially when we're talking about the bulk characteristics of the active materials, and in this case, electrodes. And the main focus of today's talk is actually being centered on the characterization of the bulk of the active materials, both electrodes in the battery cell. And of course, with this one, considering the large-scale facilities and, let's say, the best promising tools, the synchrotron and neutron techniques, which actually, due to the high energy high energy X-rays and also neutrons, can penetrate the matter much deeper and provide more deep information on the structural, compositional, and morphological characteristics of the given material. And it is my great pleasure to introduce our today's speaker, so Dr. Sandrine Lyonnard, who will actually give a talk on this topic. And Sandrine is a research director at CNRS in Grenoble, and she's a deputy head of the Functional Materials Synthesis, Structure and Properties Lab. So Sandrine is a soft matter physicist, and she is specialized in the study of structure transport interplay in nanostructural, hierarchical, and ionic materials. She received her PhD in physics in also University in France in 1997, and her habilitation in 2011 at University of Joseph Rouet in Grenoble. And her research is dedicated to the development of scattering, imaging, and spectroscopic ex situ, in situ, and operando techniques at large-scale facilities for the characterization of the fuel cells and battery components and systems. To go a little bit more deep, the focus is set actually on the in-depth understanding of the basic mechanisms, as you can see here, and understanding the structure transport relationship on conducting materials, as well as operando characterization of fuel cells. Like I mentioned, it's a large-scale facilities, and operando characterization of batteries using neutron and synchrotron techniques. And actually establishing the structure property relationship in complex nanomaterials that are used for electrodes and electrolyte requires advanced characterization techniques, which are capable to provide structural, chemical, and morphological information over a large range of length scales, and possibly in real time while the device is being in function. And in order to better understand the reaction mechanisms, transport, and aging in single components and fuel devices, in recent years, Sandrine was mostly focused on operando characterization of lithium-ion batteries, and in particular, polymer-based electrolytes, high-energy cathodes, and silicon-based anodes. And today, Sandrine will address the accelerating battery characterization using neutron and synchrotron techniques, with trying to answer the two very vital questions, why and how, on the case of silicon anodes for lithium-ion batteries. So Sandrine, we are very much looking forward to your presentation.
Thank you. Can you hear me, Isidora?
Yes, yes, I can hear you very well.
Perfect. I will share my screen.
Yes, thank you.
Okay, hope you can see it.
Yes.
Perfect. So good afternoon, everyone. I'm delighted to give this talk this afternoon. I want to thank Battery 2030 Plus and Christina Edström for the kind invitation, and you, Isidora, for the nice introduction. Thank you. Of course, it's my pleasure also to talk on the 8th of March. This is Women's Day. I want to say a few words. I'm convinced that we all have a role to play in terms of communication, education, training, mentoring, to bring more women into science, more women into battery science, maybe more women into physics, which is still a challenge. And in general, I would like to dedicate this seminar, if I may, to women who fight for their rights in their careers, and also in this kind of chaotic times in Europe, to women who fight for their lives and their freedom. So let me start with some general context on batteries that Isidora already introduced a bit. So we are facing huge challenges in the coming decade in the development and research of batteries in terms of performance, safety, manufacturing of batteries, recycling, and so on. There are many technologies actually that rely on a large variety of chemistries. State of the art is using as anodes graphite or silicon graphite materials, which will be the main focus of my talk. In all these type of technologies and chemistries, as Isidora already mentioned, there's a large number of mechanisms, degradation mechanisms in the battery that may limit the performance and the lifetime of the device. And those mechanisms, they extend over large length scales and time scales, and they are all related, interrelated, intercorrelated. So we need tools, methods, and approaches to understand those mechanisms over those extended ranges of length scales and time scales, which basically rely on electrochemistry, of course, in-lab and large-scale facility characterization, numerical simulations, modeling, and other developments. So in this talk, I will focus on the large-scale facility characterization because neutron and synchrotron techniques are tools of choice in this field, and this is for several reasons. Neutrons and high energy X-rays deeply penetrate into the matter, and therefore you can go through casings and cells. So the little movie you see is data obtained on a real battery cell. Techniques have some chemical sensitivity. For instance, with neutrons, one great advantage is you can use isotopic contrast with lithium-6 and lithium-7. So you can probe chemical reactions and chemical environments. In the case that is shown on the screen, this is different phases of a graphite electrode during dilation. And last but not least, those techniques that provide excellent space and time resolutions. For instance, if you use nano or micro beams at a synchrotron, and so you can spatially resolve different kinds of parameters you can measure and do operamidal measurements, including at fast charging. In fact, what you can see on the screen is the depth resolved mapping of the lithiation state in the graphite electrode using a microbeam at a synchrotron. So let me show you where we are in Grenoble. This is a very nice city in France. The CA is a quite extended center of research with something like 200 people working on batteries. My lab is indicated and very close to the large-scale facilities that we are lucky enough to have in Grenoble. So the European Synchrotron Radiation Facility, SRF, and the Neutron Reactor Institut Lowe-Langevin, ILL. And so in this talk, I will show you the kind of nice experiments that we can do in these facilities. So my focus is on silicon anodes because silicon is a very important material due to its high gravimetric and volumetric capacity. However, due to the alloying reaction with lithium, there is huge volume changes of silicon during the cycling of the battery, and therefore pulverization, cracking of the particles, delamination from the current collector, or the continuous creation and cracking of solid electrolyte interface. And those three mechanisms being major causes for degradation and ultimately failure of the battery. So there's still a lot of work to do to measure, quantify, understand those mechanisms. People are trying to develop materials to mitigate them, particularly using nanoparticles or nanowires, for instance, because it has been shown that below typically 150 nanometers, you can significantly avoid the cracking of the particles, and also dispersing those particles in a conductive matrix, carbon matrix, or using dual phase composite materials as the one that is shown on the image that can help to buffer the volume expansions during cycling and keep the mechanical integrity of the electrode. So the question we have as people doing characterization is, can we probe the active materials evolutions at microscopic scales during battery cycling? So basically, we're interested in understanding the lithiation mechanism, the formation and growth of the solid electrolyte interface, and the structure and morphology of the anodes. And to do that at the large scale facilities, there are many, many techniques available that we can classify basically in four big families: surface techniques, bulk spectroscopy, diffraction and scattering, and imaging and tomography. And what I want to do in this talk is showing you some examples of one or several techniques belonging to each of these categories. Of course, I will not go into details about the methods and the results, but what I want to do is an overview such that I can give you a flavor of what are the main information you can get with all these very nice large-scale facility techniques. So I will start with my first example belonging to the category of surface techniques. So this is a study using X-rays reflectivity, which we did to investigate the formation and growth of the SEI. So in a nutshell, the principle of this technique is that you have a substrate on top of which you have a layer that you're interested in a medium. And you will shoot a grazing incidence X-ray beam on this layer, and the beam will be reflected. What you measure is a so-called reflectivity profile, and this reflectivity profile is a Fourier transform of the electronic density profile. So with such measurement, you can have access to the mean electronic density across the thickness of your layer, and you get information in terms of thickness, roughness, and average electronic density of one layer or two layers, several layers if you have in your system. So this technique has been applied recently, in particular in the case of silicon, using silicon wafer-based batteries by different groups. Here is an example from the group at Stanford, where they basically measure the reflectivity profiles. From them, they deduce the electronic density profile in different states of charge of the battery, and they are able to build a mechanistic model where they evidence the presence of several types of SER layers, and they can even prove the duplication of silicon. So this is a very powerful technique that we applied also in our group, but with a kind of different question. What we wanted to look at is the dynamics of the SEI. We used very standard carbonate electrolytes, and we built a cell that is compatible with the synchrotron technique. And the results of the measurements are shown on these 2D mappings, where basically you can see we start cycling the battery here. This is the first lithiation, and then the second, the dilithiation, and then the second cycle, and then we start the third cycle. What you see are reflectivity profiles that are stacked one on top of the other as a function of the reflection angle. And so clearly those are raw data, which without knowing nothing about the technique, you can see there is a feature that is appearing on the first lithiation and then disappearing, and with time it's coming back and disappearing again. So this is what we call the grazing SEI, and this particular colored regions are really the fingerprints of the SEI that is built during the cycling. Interestingly, if you change the electrolyte and you go to an ionic liquid, which is known to be preventing the formation of SCI. In that case, you get a completely different 2D map during the cycling, and you can notice the lack of features that are typical of the SCI. So I wanted to show you this example to highlight the benefits of these techniques. It is suitable to probe the interfacial layers, in particular SCI. If you do a quantitative analysis, you can get access to thickness and average electronic density of the layer. And what I want to point here is that different electrolytes will yield a very different SCI behavior that you can immediately visualize with your raw data. So this technique might be helping to screen SCI stabilizing electrolytes, like for instance, the ones prepared by Isidora could be, the best ones could be sent to us, and we could immediately say whether they are stabilizing or not the SCI. Of course, there's still some work to do with this technique. We are using model type batteries that are quite far from the realistic electrochemistry that we would obtain in a real battery, in a real anode. And quantitative analysis is model dependent. So with this example, I've shown you that we can see the dynamics of the SCI when it builds, but we don't really have details on the compounds that are formed during this SCI building. So to get insights into the compounds, we need another technique which belongs to the family of spectroscopy and which is called X-ray Raman scattering, XRS. The most known and used spectroscopy techniques in the field of batteries are X-ray absorption and XPS, which are very suited to provide a huge amount of information on the SCI compounds. But the XRS has some advantages. It's a bulk technique that is probing the electronic structure, but it's a non-resonant scattering, so it's not an absorption experiment. And what you do is you shoot a beam of very high incident energy in the range of 10 keV, but what you measure is the energy loss that is in the range of the binding energy of a core electron. And this allows you to measure soft X-ray spectra of the light elements, carbon, oxygen, silicon, and also lithium, which is basically not accessible by any other kind of technique at the synchrotron. So what we did is investigating silicon nanoparticles-based electrodes that we prepared in different states of cycling and lithiation, put them in a airtight cell that we had built for ID20 at the SRF. And the question is to see whether we can have insights into the lithium and silicon chemical environment. So we first look at the lithium KH that we can measure. So what you see are spectra. So those are intensities versus the energy in the range around 60 eV in the case of lithium. You have several types of data where we can compare partial lithiation and full lithiation, for instance, after the first cycle on this graph here. Or if we want to compare the effect of aging, we can compare a one-cycled electrode with a 20-cycled electrode in a fully lithiated state. You see clearly that there is a huge change in shape of the spectra, and this is telling you that the chemical environment of lithium has been very significantly affected after some cycling. Interestingly, if you compare the 20-cycled electrodes in the fully lithiated in red and in the dilithiated state in blue, you also see that there are some significant changes in the position of the features and in their intensities. And this, of course, relates to the formation of the SCI and to the aging of the material. We would like to have more quantitative analysis of these spectra, of course, and for that we need to have some references. But as I said, this technique is quite new in the field of energy and there were no references available. So we measured our own references. In particular, we measured LiF and Li2CO3, which are the main compounds forming the SCI. And you can see on the reference data that you have some very specific features at given energies. So those are our references. And now we want to fit our data, try to see if we can reproduce our data by using a convolution, a linear combination of those references. So this is what I show now. You can see the blue data, so the dilithiated state of the electrode and the result of the fit, the best result of the fit is in green. So good news is that we can capture the presence of the lithium carbonates and we can estimate the amount, so which is quite high in this case. But of course, bad news is that there is clearly some missing contributions. We can't reproduce very well the data we've measured. And this is probably due to the fact that we don't have all the environments, possible environments of lithium here, and lithium might be coordinated to different compounds. And in fact, in particular to the silicon. So if we look now at the silicon data, so at the silicon L23 edge, which is around 100 eV, what you can see is the existence of features that are typical of the lithiated phases of silicon below 100 eV, and that are typical also of lithiated phases of oxide silicon, typically below 104 eV. And you see that those features are changing depending on the state of charge of the electrode and its number of cycles. And in particular, what is interesting is that those species are not reversibly removed after 20 cycles. So there's still some, they remain present in the dilithiated state, which is of course one fingerprint of aging of these materials. So in order to go further and analyze this data at this stage, we need to have more insights, and we did modeling. And so this is a collaboration we have within the big map with the groups of our colleagues from Roma, where they have currently developing DFT simulations to establish an atlas of fingerprints for spectroscopic techniques, including XRS. And so the goal is basically to use our data to refine the models, validate the models, and also be able to treat quantitatively our data using the reference simulations that our colleagues are developing for all the different lithiated phases of silicon, as you can see here. So to conclude on this technique, it's a bulk technique, so it's very complementary to XPS, for instance. You can have access to the local chemical environment of light elements, in particular lithium. And there's still work to do because quantification is very difficult, and we need to build a database to help with these measurements in the field of battery research. There is no operando accessible for the moment because it takes basically 4 hours to take one edge on one sample. And there are some issues on beam damage that must be carefully looked at. So with the two first examples now that I've presented, you've seen we tackled the issue of measuring the SCI formation and composition. But now, what about the structure and the morphology of the silicon during battery cycling? So due to the de-alloying mechanism, core shell morphologies are produced when the lithium gets into the silicon, as you can see on the nice microscopy images, where you see that under lithiation, there is a shell of amorphous lithiated phases that is created, and the core is consumed until the end where you get a fully lithiated particle. So the question we have on our side is, can we measure in real time the characteristics of such core shell particles in terms of sizes, dimensions, but also composition of the shell? And yes, we can if we use a technique that is called a small angle scattering, in particular the small angle neutron scattering, which I will show you in a minute. So we investigated electrodes that are made of silicon nanoparticles in the range 30 to 40 nanometers. The electrodes were made using VGCF fibers as conductive agent and deuterated polymer as a binder. We designed a specific cell for this experiment, which is neutron transparent and compatible with the SANS measurement. So basically you shoot the neutron beam onto your cell that will cross the battery, and the beam will be scattered and you'll collect it on a detector. So the battery is simply an anode that is coated on the titanium plunger. They have the lithium metal as a counter electrode on the other side and the electrolyte in between. And note that we don't have any separator in the cell, not to produce any parasitic scattering for the measurement. And this results in an electrochemistry that is not perfect. Particularly, there is a huge irreversibility at the first cycle. Nevertheless, we can nicely cycle this battery in the beam and collect data, and that's what we did. And you get the real-time SANS data, which are intensities versus momentum transfer. So you see on the first graph, we're starting from the black curve that is a pristine state, and under lithiation, there is an extra intensity that is developing until the red data. And when we dilithiate, we go back and not to the initial state because of this irreversibility that I mentioned earlier. So what we want to do is analyze quantitatively this data. So the sample we have basically can be schematically represented as big VGCF fibers, very big with respect to our small nanoparticles of silicon in a medium. And the data we collect are composed, in fact, of 3 regions of interest. The first one is here, very small angles or small Q values. We have a slope that is a Q-4 slope that is well known from people doing SANS, relates to interfaces. And this is not changing much. And in our case, it's related to the interface of the VGCF fibers. On the other side of the spectrum, you have a plateau, which is a constant intensity due to the intensity from the fluid, from the electrolyte. And what we're interested in is an intermediate region, which is basically probing characteristic sizes from 1 to 150 nanometers. And this is exactly where we have our nanoparticles sitting, because they are in the range, in the pristine state of 30 to 40 nanometers in size. Usually when you do a SANS experiment, you have an intensity that is the product of 3 terms. The first one is what we call the contrast. So the contrast is basically the difference in color between your particles and your medium. So in our case, it will be depending on the scattering length density of the lithiated alloys of silicon, IRIG-SyMMES. Then there is a second term that is named the form factor that is related to the shape and size of your particles. And the last term is what we call the structure factor, which correlates to the way the silicon particles are organized together. So what we expect is that the extra intensity we see on lithiation is the changes are coming from both the composition variations during lithiation, the formation of the lithiated alloys, and also the volume expansion of the particles. So in principle, it is kind of complicated to analyze this because we have the product of 3 terms, but we can use a trick because we measure this data on an extended range of length scales. And so we can focus on separate regions of the spectra. If we look at this region here, we will be sensitive to the interface and only the interface between the particles and the medium. Therefore, we can have access to the contrast term. If we look at the intermediate regions, we will be in a range of sizes that is matching the size of our particles. So we'll have access to the form factor of the particles. And if we go to the lower Q regions in this data, then we have access to the way those particles organize one with respect to the others. So that's exactly what we do. And let me show you what we obtain if we look at the signal coming from the intermediate region, so the particle scale. From some processing and analyzing of this data, then we can extract the particle sizes during lithiation in blue and dilithiation in green. And they are represented here on this graph as a function of the potential in the measurement. So what you can see is for the medium-sized particles, they vary around from 30 to typically 42 nanometers. So they grow, of course, during lithiation, and then they decrease in size during dilithiation. And the biggest ones, they are around 42 nanometers at the beginning, and they reach up to 72, 73 nanometers at the end of the lithiation. So basically with this measurement, we have a real-time measure of the individual particles expansion. Now, if we assume that we have spheres, we can very easily calculate the volume expansion from that, and we get the following result. You have here the volume expansion as a function of the potential for the lithiation phase. So the blue points are just coming from the previous analysis, the particle level analysis of the SANS data. If we look at what we can obtain from the interfacial analysis, so looking at a different region of the spectra, we can extract the lithiation index X, and from this we can calculate the expected volumic expansion. This is shown in green. And we also have the electrochemistry from which we can get the X index also and calculate the expected volumic expansion. And what you see is that the results from the SANS data are very consistent one with the other, and consistent also with the electrochemistry. And now we can interpret a bit what we see. So we start from a crystalline silicon nanoparticle, and in the first region, 1, what we do is a continuous increase of the lithiation index. We have this core shell that is developing. Then at 60 millivolts, we have an abrupt biphasic transition up to the Li13 Si4 situation. We still have a core and a shell. And then the next step is the formation of the well-known Li15 Si4 phase with an X value of that is around 3.75. There is a last step, which we are not sure yet that we fully understand, where we see that we continue to increase the X index, which might be something like gradient or another shell that is enriched in lithium. So we still are working on that to be sure of this interpretation. So operando science is nice, you can do it. The resolution in time is good. You can acquire in 1 minute a spectrum. You can follow the nanoscale evolutions. This is very useful in many types of materials for batteries, in nanostructured materials, or you can also follow nanopores. And you get the information on the lithiated phases, including the amorphous phases. So this is nice, and there's still work to do because our cell is not optimized. There is no separator, as I said, so the electrochemistry is not perfectly reliable. And of course, this is an average technique. We are not specially resolving anything. We are just going through with a big neutron beam, going through the whole battery. So if I summarize what I've said on the structure, I've shown you this example of the small angle scattering, which is very useful to look at the core shell morphologies. I don't have time to present another study we did on similar materials where we used operando XRD, and the focus was a bit different. We wanted to look at the situation of the crystalline core in terms of strain and stress that is applied on this core by the amorphous shell when it is built. So those are two types of information that are very complementary that we can have with two techniques. And at this point, well, the question is, can we do better? And could we cover several scales in one single experiment? In a dream world, I would like to have both the SANS and the XRD simultaneously. And in fact, this is possible. And this is what I'm showing on the next example. If we combine SAX and wax techniques at the synchrotron. So this is something we have demonstrated recently on graphite silicon anodes using beamline BM2 at SRF, where you have two detectors. So it's very nice because you can put your porch cell in the beam. Your beam will be scattered, and on the first detector you can collect the diffraction pattern during operando measurement, and on the second detector you can collect simultaneously the SAX variations. So you can get simultaneously in one experiment information at the atomic scale about the crystallographic information and information at the nanoscale about the volume changes, for instance, of a nanostructured material. So we applied this technique to new materials, promising materials developed by our colleagues at CEA, where they investigate silicon nanowires-based anodes. So they prepare two types of materials. Either they blend the nanowires, so the silicon phases in white, and they blend it with graphite, as you can see that are colored on the image, or they directly grow the silicon inside onto the carbon. And you see on this image that you have a silicon phase that is located also inside the graphite chunks. And so basically the question that we were asked is, can we understand the lithiation mechanism in these complex materials that are composed of two active phases? So we performed this SAX-wax combined experiment on BM2, and what we used the two porch cells with the two different materials and looked at the first cycle. So with the wax, you can measure the diffraction. So you get the graphite states of lithiation with the different peaks. You can deconvolute, integrate, and then you can add the evolution of the graphite during the cycling, during the lithiation on the left panel, and during the dilithiation, and that for the two samples that we have. What you notice is on lithiation, for instance, you start with graphite, which is blue data, and then you form LiC12, which is the light blue. And once you have formed LiC12, you can start forming LiC6, and at the end of lithiation, you finish with a fully lithiated electrode with graphite in the shape of LiC6. When you dilithiate reversibly, well, you lose LiC6, you form LiC12, and continuously you will end up with a fully dilithiated graphite electrode. What is interesting is you see the boundaries of the different regions is not the same in the two samples. The mechanism is exactly the same, but the boundaries are changed. And this is just due because we had a different amount of silicon in those two materials. And we combine this with the SACS because we have a second detector, so that's nice. And now we can look at the SACS data, which look like very much what I've shown on my previous example using when I described the small angle neutron scattering analysis. This is basically the same kind of data. And so we look at this extra intensity here that is due to the lithiation of the nanowires. We process a bit the data such that we can integrate the regions of interest where there are major changes. And what we do is we plot the variations of the integrated intensity during lithiation and dilithiation for the two samples, so for the composite in red and for the blend in black. And now what we have to do, and what is very nice, is you correlate the nanoscale expansion of the silicon to the graphite situation, and you see that the boundaries fall exactly on the same, on regions where things are changing. So if you look at the, for instance, the dilithiation here, the signal is not changing on the SACS intensity in red until you have fully dilithiated your graphite. And at that point, you can start to have a decrease of the intensity that corresponds to the lithiation of the silicon. The same for the black sample. Nothing is happening until the limit here where you have completely dilithiated your graphite, and then you start dilithiating the silicon. So those changes in slope in the SACS data, they are really telling you the interplay between the silicon and the graphite lithiation and dilithiation, and you can establish the sequences of steps for the lithiation of this of the two phases. So this technique is really nice. You can do operando. You have atomic and nanoscale in one shot. And this is very useful to establish a sequential mechanisms in complex materials, in particular in composite materials. I want to mention that you can do this on lab pouch cells, but you can also look at industrial pouch cells and even look at this very high C rates because the time resolution is excellent. It is especially averaged technique as the one I've shown before, because it's in transmission geometry, so your beam is just crossing all the components. And of course, if we want to have more detailed analysis of the shapes of our signals, in particular here on the SACS data for the silicon, we would need the help of some Newman type modeling of the electrode, and that's what we're currently developing also in our lab. Okay, so at this point of my talk, I've shown you different examples of surface techniques, spectroscopy, diffraction, and scattering applied to different types of silicon anodes. We can get different types of information like sizes, strain, mechanism, compounds. And of course, the next question would be, can we spatially resolve those measured parameters or information, which means can we understand the distribution of those parameters in the volume or in the thickness of an electrode. And this is exactly what we can do by applying the last family of techniques, which are imaging and tomography techniques. So I want very briefly to introduce two techniques. One that is a SACS-WAX tomography. So it's a kind of follow-up of the previous example. We had SACS-WAX, we were very happy, but we can do even better by applying tomography. I will show you in a minute. And the second example will relate to neutron imaging. So we want to do SACS-WAX computed tomography because we want to resolve heterogeneities in the volume of an electrode along the cycling. And we want to map, if possible, the distribution of lithiated phases. The materials we were working on in this project is a composite again. So we have graphite particles and we have a silicon phase that is not made of nanowires in that case. But it's a very complex phase. It's a composite with amorphous silicon channels in between in a kind of matrix that is composed of almost inactive crystalline iron silicide particles, which are here to buffer the silicon expansion. Those materials behave quite well in coin cell. Actually, after 150 cycles, you still have 70% of capacity retention, which is not bad for such kind of high silicon content material. And so we designed the computed tomography experiment to look at in details what happens in these materials. So we had first to design a cell. It's a Swedge-Lock type cell, which is very simple. You have the current collector, your anode, the separator in blue, then the lithium metal. And what you do is you locate this cell in the beam. So the beam is coming from the tube. You can vertically move your cell, so you can select precisely the region in your electrode where the X-rays will hit the electrode. And once you've selected the height you want to investigate, what you do is you rotate your cell and you make what is called a tomography experiment. And then on this beamline ID31, you can have the wax and the sacs. You can have two detectors you can use. So this is very interesting. And if I show it again in a more 3D expanded view, our cell is like this. We have a 50 micron thick electrode. And what we do is we select 3 positions in the middle of the electrode, close to the current collector and close to the separator. So we select 3 positions in height and we do the tomography. We get a slicing of the data. So what we did is doing that operando, we cycled the cell at C/10 or followed by C/5, and we make the measurements during OCV at the 3 Z values that I indicated on the graphs. And basically what we measure is the following. We get slices. So let's look at the example of the slice that is in the middle of the electrode. We get 2 types of slices. From the wax data, we get graphite information. So we get the state of lithiation in graphite, X in the LIX-C6 phase. And from the silicon, we get the state of lithiation of silicon, X in the LIX-Si alloy. And you see clearly the shape of the electrode that is round. And this is partial lithiation first. So you start lithiating graphite and a bit of silicon. And when you finish your lithiation, well, you see you have lithiated both the graphite and the silicon. And you can see also that the lithiation is not completely homogeneous. It is more lithiated in the center of the cell, which is probably due, of course, to the geometry, the Swedge-Lock geometry. You further delithiate now. You do first the partial delithiation, and then you do the full delithiation, and you get those results. So at partial delithiation, you see you have fully delithiated the graphite, and you still have a lot of lithium in the silicon. And then at some point you can delithiate silicon, and at the end you get a fully delithiated electrode. You can start again a lithiation with a different C rate if you want to investigate the effect of C rates. I will not show that, but then you have again the lithiation, second lithiation data. So basically this is nice. You again measure the sequential delithiation mechanism in these materials, graphite and silicon. We see heterogeneities at the surface. We can make more quantitative analysis by looking at selected pixels if we want. And interestingly, we have those data for the 3 slices. And the next question is what happens during relaxations? In fact, experimentally, what we do, taking here the example of the sequence where we stop at 5 millivolts. So we are lithiating our electrode, we stop, we pause electrochemistry, and we make the TOMOS measurements. And what the TOMO is taking 1 hour, we have 3 of them to do in sacs, and we have 3 of them to do in wax to get the full picture. So in total, we have 6 hours of measurement. And during that time, the potential is relaxing a lot. The battery is relaxing a lot, and the potential is reaching values up to 120 millivolts. So not only we have spatial heterogeneities in this data, which is what we were looking for, but we also have time heterogeneities because the system is not at equilibrium. And now we can look at the effect of this relaxation because we perform Z scans, so not tomographies, only vertical scans in the batteries at 3 different points that are indicated by the stars. And let me show you the result. So we have our battery, our anode, that is in between the separator and the current collector. The black squared shapes show you the different positions, different lithiation state of the graphite. So the more it is black and the more it is lithiated. And the red is the silicon. And this is the first point. So we are at 86 millivolts already. And then we can see the results from the second and from the third points that we have measured during the relaxation until 120 millivolts. And what is nice is you can clearly see that there are some variations, there are some gradients. And what happens in particular in some regions of the electrode, you can clearly see that you lose some lithium in the carbon, in the graphite, and while you are gaining lithium in the silicon, which is getting more and more red. So you see with this experiment, the homogenization during the relaxation step between the different phases. And this is in line with the literature where people have shown that, in fact, during relaxation, the graphite is expected to give its lithium back to the silicon. So to wrap up on this technique, we can do operando on switch-locked cells, so quite nice cells for the electrochemistry. We get the atomic and nanoscales in one shot, and we can have specially resolved up to 3D potentially mappings. And this is very useful for component-specific contributions and internal dynamics inside the electrode. The time resolution was not very good at the time, but has been much improved now on the experiment. So we are expecting to do even much better now on ID31. The last example I want to show is now making progress towards the even more complex use of the large-scale facilities. And this is a multimodal characterization. Multimodal means you will combine neutrons and X-rays. So this is a measurement that is possible at ILL on the instrument next, where you can do neutron imaging, and they have an X-ray tube, and you can also do the X-ray computed tomography on the same battery in the same location, in the same experiment. So that's what we were doing on commercial cells, which are rolled cells. You see a top view of the cell here, and the bottom view of the cell. The side view of the cell, sorry, for the X-rays on the left and for the neutrons on the right. Of course, the contrast is not at all the same. X-rays will be very sensitive to the metals. So in particular, we will see very, very well the current collectors, while the X-rays the neutrons are extremely sensitive to lithium. Lithium is a strongly absorbing element. As soon as you will have lithium in the beam, you will see it. So basically what Eric is doing is in this work is first of all, aligning the slices coming from the neutron computed tomography to the data coming from the X-rays computed tomography, is aligning them and producing this nice colored image where you have signal coming from the X-rays in red. And in particular, you see the very thin layers, the thin lines correspond to the current collectors, the copper current collector here, and the aluminum nearby, while the cyan color is related to neutron data and therefore to basically lithium in the materials. And there are two batteries shown here. This one here is a pristine battery, and the other one on top is the battery after 700 cycles, where you see that there has been some significant changes that we can further look by performing a virtual unrolling of the battery. You can see now the battery when it has been unrolled in the discharge state after 700 cycles. You can compare this to the one that is charged in a charged state. And if you want to look more, you make a zoom and you see very typical features of aging, like, for instance, regions where the current collector is bent here. Regions that are darker, or even holes where it means that you have disconnected some regions that are not anymore active. You saw also regions where it seems you have a nice cyan layer, which means you have some lithium plating, or at least very enriched lithium layers. And everywhere you have gradients in the cyan color, which means you have distributions of lithium inside the elements. You can quantitatively look at that by doing some slicing in this data, and you get some profiles on the two cells at different locations in the cell. And of course, this is the attenuation is proportional to the amount of lithium you have in your cell. So this is a very nice technique. You can really identify defects after long-term aging. You can look at the lithium trapping in the various elements and locate the space distributions of lithium in industrial cells. Of course, this is there are millions of data to analyze, of profiles to analyze. So you need machine learning-based methods to get some statistical analysis and get some quantitative output parameters, which is a work that is currently ongoing. And with this, I reach the end of my talk because I want to wrap up and summarize what we've learned on silicon. So I've shown a number of examples. All these are single shot experiments. They are typically performed on one type of battery or one type of material, one technique, one scale, one type of information. So there's lots of data that we can have, but it's still a fragmented knowledge. And we would like to have a more, let's say, multi-scale picture of the situation of the degradation mechanisms and basic mechanisms in the battery. So I see a few challenges to reach that goal. Challenge number one is the standardization of cells, because all the results I've shown, you've seen that have been taken on different kinds of cells, different kinds of protocols for cycling that were applied and so on. So it's very difficult to compare the results. The second challenge is we would like to have a more holistic approach because we want to see the tree and not only the individual leaves with a lot of details. And so we need to combine and couple techniques. And well, the situation of a standard single shot experiment at the large scale facility is a sequence of actions. It is a linear sequence of actions that I'll show here on the example of the XRD investigation of strain in silicon nanoparticles. You get your sample, you get your question, then you select the best beamline, you apply for beam time, you submit a proposal. If you are lucky, you get granted, then you develop your operando cell in the meantime. You perform your experiment and acquire a number of real-time XRD patterns. In that case, then you need to analyze, you need to fit the data, and you get at the end the output parameter, which in that case was the evolution of strain in the core of the silicon particle. And happily, you can publish this result. And this is very time consuming and takes on average 18 months and even can take even more. It's even more complicated when you do coupled experiments. So the two I showed, for instance, the SAXWAX or the NCT-XCT. In the example of the SAXWAX tomography experiment, you had your sample and your question, submit the proposal to ASRF, get the beam time, perform your experiment, which is acquiring a huge amount of data, and then you need to do the analysis of this huge amount of data. And what is difficult is to do correlative data analysis of multiple data sets. So the timeline of the single shot experiment was 18 months. And if you want to have coupled or combined experiments, it may extend even more further than 2 years. So basically, it is too long. We should do better. We should do faster. And this required to invent new tools, new workflows, new modes of cooperation, and somehow think out of the box. And if we want this holistic approach in the characterization of batteries, well, one first consideration is we need new modes of access to the large-scale facilities to reduce the time for this sequence of actions that we have in the development of a single-shot experiment. In this context, we started in Grenoble a collaboration with ISRF and ILL and proposed a concept of Grenoble Battery Hub, which is a European platform for characterization of batteries at the large-scale facilities. The aim is to develop multimodal, multi-techniques characterization in a way that it would be more flexible, versatile, reactive, with repeated access to instruments, and that would be grounded in long-term research programs instead of standalone experiments as it is now. And the concept of the hub is that it would secure beam time for a community, for the community of battery researchers, and the proposals would be peer-reviewed by the community itself. So it's a big change in habits for both battery scientists and the large-scale facilities. We are now in the first stage of this project where we operate a pilot phase where we want to test the mechanism. So basically we have 70 shifts that we distribute every 6 months to all the CEA teams. This amounts to something like 10 experiments. And what is important is that this project will be, this hub will be opened to European partners, and there will be a call as soon as we have defined test mechanisms. And so if you are interested, if you want to join the initiative, please contact us and we can get more details. So once we have this type of mechanism that starts being developed, we can think about what we need to develop a multimodal and multi-scale standardized experimental workflow. The dream vision is the following. We would like to have a standardized battery cell that is compatible with several beamlines. It could be equipped with sensors, for instance. It could be a smart battery. We want to have several types of detectors because we want to access chemical information, morphological, structural, electronic properties, and so on. We may want to have several beams on it, neutrons or X-rays, depending on the question we have, maybe something else, maybe electrons, lasers. We might need to have several beams, several batteries in the beam to optimize the use of the beam time, and also because we need to have some capabilities for high throughput experiments. We would need the raw data to be correlated on the fly and processed and sent to an artificial intelligence that would interrogate database and modeling, and be able like that to feedback loop to the control of the experiment and select the best detector, the best sample, the best beam for doing the best experiment. At that point, we have created an automated data acquisition loop. And of course, we need to make it efficient, an automated data analysis loop. And this would build a new facilities where we need to have dynamically refined multimodal standardized data sets. We need to dynamically refine the correlative data analysis, which is extremely challenging, and to get the results in a much faster and more efficient way. So basically, at the heart of this process, there are some accelerators. First one being the standardized cell, standardized operating protocols, such that we can operate this combined experimental workflow. We need on-the-fly setup control, and we need new apps, software, machine learning, and deep learning tools in the automated data analysis. And at the entrance of this mechanism, we have those new modes of performing experiments at the large-scale facilities in terms of hubs or science-driven long-term proposals, which allow to have an array of techniques that you can use on an array of samples, trying to answer an array of questions and not only single-shot experiments. So with this, I'm done. I just want to take the opportunity to advertise for the International Grenoble Battery Days we are organizing with Claire Vivier in Grenoble in France in May. This will be in person. We are very happy to have a list of very distinguished speakers. And so the abstracts deadline have been extended. If you're interested, please submit your abstract. And want to thank all my collaborators, the funding bodies, and particular thanks to the people who are helping us on the large-scale facilities, so the beamline scientists. I want to mention Jakub Nemes on ID31, Lionel Porcard on D22, Niels Blanc on Saxwax BM2, Samuel Tardif on the XRD, Christophe Salé, Alessandro Longo on the XRS, and Lucas Elfen on the imaging next at ILL. And thank you all for your attention.
Thank you, Sandrine, for this great talk and providing us a very comprehensive overview on the complementarity of the techniques and, let's say, puzzling all the pieces together and also providing the whole picture. So not only stressing the limitations and challenges of each method, but also trying to get the whole picture together with the different, let's say, approaches from different techniques, and also correlating them to the theoretical support and theoretical correlations, which we find to be quite important for the further development of the battery chemistries. So thank you once again. Thank you. Yes, so we have one question. The concept of the battery hub is really interesting. Can you comment whether similar initiatives exist in US or Asia? Also, what is the level of competitivity with respect to battery research when one compares large-scale infrastructures available in Europe with respect to US or Asia?
I am not aware of such hub concept in the US or Asia. The facilities are usually national facilities, and they are very much connected in the US with some labs. This is the way it works. So Argonne or other places, Berkeley. They are usually connected to electrochemical labs and teams working in the field of battery. What we propose is different. It's really a new conceptual way of using the beam time for a community. So this is inspired somehow by something that is existing in structural biology. But it's much more complicated because we now want to have access to a huge amount of beam lines, and the community is also very large. This is for the first part of the question. Second part of the question, I don't remember exactly.
So the level of competitivity respect to battery research when one compares large-scale infrastructures that are available in Europe and in Asia and US.
Well, I'm not sure I can really answer this question, but what I can say is that ESRF and ILL are the most powerful tools in the world. This is not because they are in France, not because they are European. I think this is just that ESRF is the first synchrotron of fourth generation. There will be others. So it offers really a super high brilliant beam with extreme coherence, and there are some beam lines I mentioned in my talk are unique in the world. And it's regarding neutrons. I mean, ILL is the most powerful research infrastructure for research nuclear reactor for research. So I don't want to say those are the best instruments in the world, but in terms of competitiveness, I think the experiments you can do at ILL and ESRF are really top class experiments because you benefit from the best beams, among the best beams in the world.